Hello and welcome to online lecture number 11 for Chemistry 1101 during the spring semester of 2020. In this lesson, we're still in Chapter 9. Chapter 9 is all about solutions, understanding how to quantify solutions, describe solutions, and ultimately, as we'll get into in this and the next lesson, how to predict the properties of some of these solutions. The last couple of lessons have been mostly concerned with various ways of describing the concentrations of solutions. And the ways we looked at were percent concentration, mass over volume percent as one of those examples, or much more commonly, much more useful, generally speaking, is the molarity of the solution, the ratio of the number of moles of solute per liter of solution. And we're interested in describing the concentration of solution and being able to express the concentration of solution quantitatively in this way, because for the solution itself, most of its properties, at least many of its properties, can be predicted based upon both the identity of the solute, so what the solute actually is, as well as its concentration. So a couple of very common examples of that might be the color of a solution. Imagine if you have a colored solution prepared by combining a drop of blue food dye with water, and then you add another drop of food dye, blue food dye, and another drop of blue food dye. So obviously the color will change, color will intensify as the concentration of the blue food dye increases. The smell of a solution also would depend upon whether the solute has a smell, as well as its concentration, how much solute is present. The taste of solutions would also, for much the same reason, depend upon both the identity of the solute, whether the solute itself has a taste to it, as well as how much of that solute is present. And just generally speaking, most of the chemical reactivity, most of the chemical properties of a solution would depend upon both the identity of the solute as well as its concentration. And so those are just 4 examples of properties of solutions which depend upon both the identity of the solute as well as its concentration. But there are some properties, and these are the properties we're going to concern ourselves with in this chapter, some properties which only depend upon the concentration of the solute. In other words, these properties do not depend upon the identity or what that solute actually is. It only depends upon the concentration of that substance. And these properties which only depend upon the concentration of solute, not its identity, are called colligative properties. And the next lesson, we're going into more details about what these colligative properties are and how we can predict these relative colligative properties. So these colligative properties are only going to depend upon the number of solute particles dissolved in the solution, not in the identity of those particles or the nature of those particles. So just kind of introduce these colligative properties. What we'd find and what we'd learn is that the colligative properties of a 1 molar sodium chloride solution would in fact be the same as the colligative properties of a 1 molar potassium fluoride solution. Well, maybe that makes sense because they're both 1 molar solutions, so maybe that's our answer to why they have the same colligative properties. But these same colligative properties for the sodium chloride and potassium fluoride solution would also be the same for a 2 molar sugar solution or 2 molar sucrose solution. Well, that by itself tells us that it's not the molarity of the solution that's going to tell us what the colligative properties are, because whereas these molarities are the same, this molarity is different, even though this says that the colligative properties are the same. And then also these would be different than a 1 molar sodium sulfate solution. So as we'll see, molarity has a part to play, but it's not the entire answer as to what these colligative properties are and how to predict them. And the reason has to do with what happens to these particles, as we talked about in the last lesson, what happens to these substances when they do dissolve in water. So sodium chloride, as an ionic compound, will break apart into its cation and anion, specifically 1 sodium ion and 1 chloride ion. But of more importance, notice that for every 1 sodium chloride, it produces a total of 2 particles, 1 sodium, 1 chloride, but more importantly, a total of 2 particles. So we'd say that there are 2 dissolved particles produced for every 1 mole of solute that dissolves. With potassium fluoride, similar idea. 1 potassium fluoride will break up into 1 potassium and 1 fluoride ion for a total, like with sodium chloride, a total of 2 dissolved particles. With sodium sulfate also as an ionic compound will break apart into its ions, sodium ions, sulfate ions. But as we learned in the last lesson, this has to be balanced. So this subscript 2 here becomes this coefficient 2, which tells us that This equation tells us that for every 1 mole of sodium sulfate that dissolves, it produces a total of 3 moles of particles. 2 moles of sodium plus 1 mole of sulfate for a total of 3. And then for a molecular compound like sugar, C12H22O11, as we learned in the last lesson, because these molecular compound molecules simply separate from each other, they otherwise stay intact. For every 1 mole of sugar molecules that dissolve, it produces exactly the same number of moles, in this case 1 mole of dissolved particles. So this is going to be our key to helping us go from molarity to ultimately osmolarity, which is going to help us determine the relative colligative properties of solutions. So the colligative properties will depend upon something called osmolarity. Osmolarity is defined as the ratio of the number of osmoles of solute per liter of solution. And this is a very similar definition of molarity, which was moles of solute per liter of solution, but this is osmoles of solute per liter of solution. So osmoles is another way of describing the amount of solute you have. Well, the obvious question then is, well, what is an osmole? Well, an osmole is the product of the number of moles of solute times the number of dissolved particles produced when that solute dissolves. So if we combine these two definitions, we get this very useful definition, which says the osmolarity of a solution, which is the concentration unit that's going to help us predict these relative colligative properties, is simply the product of the number of dissolved particles times the molarity. And this will, so we'll go through a couple examples from the previous slide and then do some on our own. So for sodium chloride, it breaks apart into 2 particles. So 1 sodium ion, 1 chloride ion, but the important part is 2 total particles. So as a result, a 1 molar sodium chloride solution, its osmolarity would be the number of particles produced, 2, times its molarity, which is 1. So a 1 molar sodium chloride solution is the same thing as a 2 osmolar sodium chloride solution, because we just take the molarity and multiply that molarity by the number of particles produced. So 1 molar sodium chloride gives us a 2 osmoles per liter sodium chloride solution. Likewise, a potassium fluoride, like we saw, it breaks up into 2 particles. So a 1 molar potassium fluoride solution, the concentration times the number of particles, 2 times 1, also gives us 2 osmoles per liter potassium fluoride. So the reason why, we saw on the previous slide, that the 1 molar sodium chloride solution has the same colligative properties as a 1 molar potassium fluoride solution is not because they have the same molar concentrations, but it's because they have the same osmolar concentrations. With sodium sulfate producing 3 particles total per mole of solute dissolved, a 1 molar sodium sulfate solution would be the concentration, 1 molar, times the number of dissolved particles, 3. In other words, to give us a osmolarity of 3. So a 1 molar sodium sulfate solution is also a 3 osmoles per liter sodium sulfate solution. So once again, the reason why this 1 molar sodium sulfate solution has different colligative properties compared to these 1 molar solutions is not because the molarities are the same, because they are, but because their osmolarities are different. And it's the osmolarities that's going to help us predict these colligative properties. And then finally, with this sugar solution, it produces 1 dissolved particle. So as a result, a 2 molar sugar solution, 2 molar times 1 dissolved particle per mole, will give us an equivalent 2 osmole per liter sugar solution. So for these molecular compounds like sugar, because it always produces 1 dissolved particle per mole, the osmolarity for these covalent compounds or molecular compounds is always going to be the same as their molarity, same magnitude. So we'll finish up with a couple of practice examples of determining the osmolarities of various solutions. And the next lesson will then apply this new unit of osmolarity to predict and explain the colligative properties of various solutions. So we have, number 1, a 0.5 molar lithium bromide solution. And we want to determine for this lithium bromide solution what its osmolarity is. So to do that, part of that is determining how many particles are produced when 1 mole of the solute dissolves. So lithium bromide is an ionic compound. As a result, when it dissolves, it'll produce 1 lithium ion and 1 bromide ion for a total of 2 particles. So as a result, to find the osmolarity of this 0.5 molar lithium bromide solution, we take the number of dissolved particles, 2, we multiply that by the molarity, and that gives us an osmolarity of 1.0. In other words, a 0.5 molar lithium bromide solution has an osmolarity of 1.0. Likewise, for the next example, 0.5 molar magnesium sulfate, we want to determine what the osmolarity is of this solution. So that starts with determining how many particles are produced when 1 mole of the substance dissolves. So when 1 mole magnesium sulfate dissolves, it produces, as an ionic compound, it breaks up into its individual ions, magnesium ions and sulfate ions. And notice 1 magnesium and 1 sulfate for a total of 2 particles. So as a result, to calculate the osmolarity of this solution, we'll take the number of dissolved particles, 2, and multiply that by the given molarity. So 0.5 times 2 also gives us a 1.0 osmoles per liter solution. For 3.0 molar C6H12O6, this is different from the previous 2 examples. C6H12O6 is composed entirely of nonmetal atoms. As a result, we may conclude that it's a molecular compound. As a molecular compound, then we can make some predictions about how it's going to behave differently compared to ionic compounds. Specifically, as a molecular compound, when it dissolves, these individual molecules simply separate from each other. So when it dissolves, it produces exactly the same number of dissolved particles as the number of moles of solute. So as a result, when a molecular compound dissolves, we always get exactly 1 particle produced. So consequently, 1 dissolved particle times its molarity, 1 times 3.0, gives us a 3.0 osmoles per liter. Remember, for molecular compounds, their osmolarity will always be the same magnitude as the molarity. Our 4th example is 0.25 molar potassium phosphate. Potassium phosphate is an ionic compound. As such, it's going to break apart into its individual ions. Its cation is potassium. Its anion is phosphate. But notice from the formula that for every 1 phosphate that's produced, it also produces 3 potassium ions. So in order to be a balanced equation, we have to indicate that as it produces, yes, it produces potassium, but it produces 3 potassium ions and 1 phosphate ion. So in total, and that's what's important here, is a total, 3 potassium ions plus 1 phosphate ion gets a total of 4 particles. So for every 1 mole of potassium phosphate dissolves, it produces 3 moles of potassium and 1 mole of phosphate for a total of 4 moles of dissolved particles. And it's that 4 moles of dissolved particles that's going to help us calculate the osmolarity of the solution, and the osmolarity of the solution helps us explain these colligative properties. Consequently, then, the osmolarity of a 0.25 molar potassium phosphate solution will be 4, the number of dissolved particles produced, that number times its molarity, so 4 times 0.25 gives us a 1.0 osmoles per liter solution. And finally, a 1 molar barium hydroxide solution. Barium hydroxide is another ionic compound, so I break apart into its two ions, cation and anion. The cation is barium. The anion is hydroxide. But notice that for every 1 barium produced, we have 2 hydroxides. So it's expressed as part of the balanced chemical equation, 1 barium plus 2 hydroxides for a total of 3 particles. And now that we know that when barium hydroxide dissolves, it produces 3 particles, the osmolarity of a solution will then be 3 times its molarity. So 3 times 1.0 gives an osmolarity of 3.0 osmoles per liter. So these are examples of various molecular compounds and ionic compounds, how to go from the molarity solution to its osmolarity. And just to reiterate, the reason why we're interested in this new unit of osmolarity is because it's this new unit of osmolarity that will help us predict these colligative properties. So based upon then these osmolarities specifically, which solutions would we expect have identical colligative properties? So take a moment to think about that. And then recall that the solutions which have identical colligative properties, based upon what we've said so far, is that identical colligative properties depend upon and relying upon identical osmolarities. So the solutions which have identical colligative properties would be those solutions which have the same osmolarities. May have different molarities, but what's important is they have the same osmolarities. So as a result, in these 5 solutions, solution 1, 2, and 4 would expect to have the same colligative properties. Even though they're composed of different types of solutes, their osmolarities are the same. Likewise, solution 3 would be expected to have the same colligative properties as solution 5. Once again, because they have the same osmolarity values.